December 16th, 1944. The Ardennes Forest, Belgium. Snow fell in thick curtains across the frozen ridgelines, muffling the thunder of distant artillery. In a concealed gun position carved into the hillside, Obergefreiter Klaus Hoffmann pressed his eye against the rangefinder, his breath crystallizing in the pre-dawn darkness. Around him, the crew of the 88mm flak gun worked in practiced silence, men who had survived Normandy, who had retreated across France, who now prepared for what their commanders promised would be Germany's final, desperate thrust westward. The gun's barrel pointed skyward at a 40-degree angle, tracking coordinates shouted from the observation post. Hoffmann had been doing this for 3 years. He knew the mathematics of ballistics the way a pianist knows scales. He understood the parabolic arc of high-explosive shells, the predictable scatter patterns, the necessity of direct hits or near misses within a 5-meter radius to achieve lethal effect. What he did not know, what he could not possibly have imagined as he loaded the next round, was that the Americans had rewritten the fundamental laws of aerial warfare. That morning, as German forces launched Operation Wacht am Rhein, the largest offensive in the Western theatre since D-Day, Hoffmann would witness something that defied every principle of gunnery he had learned. He would see shells exploding in empty air, detonating with impossible precision directly above their gun positions without any visible trigger. He would watch his comrades torn apart by shrapnel raining from the sky like steel hail, and he would understand, in those final terrible moments, that Germany was no longer fighting an enemy, it was fighting the future itself. The Battle of the Bulge began as Hitler's last gamble, a massive armoured thrust designed to split Allied forces and capture the vital port of Antwerp. For the German High Command, it represented a final opportunity to demonstrate that the Wehrmacht remained a formidable force, that technological inferiority could be overcome through tactical audacity and the fighting spirit of German soldiers. But what German commanders did not fully comprehend, what their intelligence networks had failed to detect, was that American industry had achieved something previously thought impossible. In laboratories and proving grounds across the United States, scientists had miniaturized radar technology to fit inside an artillery shell, creating what would become known as the VT fuse, the proximity fuse, the weapon that would transform anti-aircraft gunnery from an art of prediction into a science of certainty. The Germans knew the Americans possessed industrial capacity that dwarfed their own. They had seen the endless columns of Sherman tanks, the fleets of bombers that blackened European skies, the mountains of supplies that seemed to materialize wherever American forces advanced. But material abundance was one thing. A fundamental breakthrough in weapons physics was something else entirely. The proximity fuse represented a threshold crossing, a demonstration that American technological superiority had reached a level where individual weapons systems could think, could sense, could make split-second decisions faster than any human gunner. The development of the proximity fuse began in 1940, when British scientists, desperate for a solution to German bomber raids, approached American researchers with a seemingly impossible challenge: create a fuse that could detonate an anti-aircraft shell at the optimal distance from its target without requiring a direct hit or timed detonation. The problem was both conceptual and practical. Traditional anti-aircraft fire relied on either impact fuses, which required direct hits against fast-moving aircraft, or time delay fuses, which required gunners to calculate the precise moment of detonation based on estimates of target altitude, speed, and trajectory. Both methods were inefficient. Studies showed that during the Battle of Britain, British anti-aircraft guns fired an average of 20,000 rounds for every German aircraft destroyed. The mathematics were brutal and undeniable. Anti-aircraft gunnery was a probabilistic endeavour with catastrophically low success rates. What was needed was a fuse that could detect when a shell passed near an aircraft and trigger detonation automatically at the moment of closest approach. The solution required miniaturizing radio transmitter-receiver technology to survive the extreme forces of artillery, firing accelerations exceeding 20,000 times the force of gravity while remaining reliable enough to function in combat conditions. It required vacuum tubes small enough to fit inside a 5-inch shell casing, yet robust enough to withstand physical shocks that would shatter laboratory equipment. It required power sources, timing circuits, safety mechanisms, and antenna systems all compressed into a device no larger than a man's fist. American engineers, working in facilities operated by the National Defense Research Committee, achieved what many European scientists considered impossible. They developed vacuum tubes with filaments so fine they resembled spiderwebs, housed in shock-absorbing materials that could cushion the brutal forces of artillery discharge. They created miniature batteries using reserve electrolyte that activated only after firing, preventing deterioration during storage. They designed antenna systems integrated into the fuse nose that could transmit radio waves and detect reflections from nearby objects. By 1942, the first functional proximity fuses were being tested at the Dahlgren Naval Proving Ground in Virginia, and by 1943, they were being deployed aboard U.S. Navy vessels in the Pacific Theater. The results were extraordinary. Ships equipped with proximity-fused anti-aircraft shells saw their effectiveness against Japanese aircraft increase by a factor of 3 or more. What had required thousands of rounds could now be accomplished with hundreds. But the weapon remained a closely guarded secret. Allied commanders, terrified that a dud shell might fall into enemy hands and reveal the technology, restricted proximity fuse use to naval engagements where unexploded ordnance would sink into the ocean. The fuses were not to be used over land, where German recovery teams might retrieve intact examples and reverse engineer the technology. That restriction held throughout the Normandy invasion, through the liberation of Paris, through the autumn campaigns that pushed German forces back toward the Rhine. But in December 1944, when German panzers smashed through American lines in the Ardennes and threatened to reverse months of hard-won gains, the restriction was lifted. For the first time, proximity fuses would be used in land-based artillery bombardments, and German forces would experience the full terror of weapons that could reach down from the sky with surgical precision. Obergefreiter Hoffmann understood that his position was vulnerable. Anti-aircraft guns, by their nature, revealed themselves when firing. The muzzle flash of an 88mm gun could be seen for kilometers, the sound of discharge carried across frozen valleys, and American counter-battery radar could track shell trajectories back to their origin points with frightening accuracy. But Hoffmann and his crew had developed survival tactics over years of combat. They fired in short bursts, relocated frequently, used terrain features to mask their position, and relied on the statistical improbability of counter-battery fire, achieving direct hits. Traditional counter-battery doctrine required American gunners to calculate German gun positions, estimate range and bearing, and then fire salvos of time-fused or impact-fused shells, hoping to saturate the target area. It was an inherently imprecise process. Even when American shells landed near German positions, the effectiveness depended on fragmentation patterns and blast overpressure, both of which diminished rapidly with distance. A shell exploding 20 meters away might be deafening and terrifying, but not necessarily lethal to men in covered positions. A shell exploding 5 meters away was dangerous. A shell exploding directly overhead was catastrophic, and that was exactly what proximity fuses enabled: explosions that occurred not when shells struck the ground, but when they passed directly above their targets, transforming every artillery round into an aerial burst optimized for maximum lethality against exposed personnel. The first American counter-battery salvo arrived 17 minutes after Hoffmann's gun opened fire on Allied positions. He heard the distinctive whistle of incoming 105mm shells and shouted for his crew to take cover. Standard procedure. The men dropped into their protective positions, covering their heads, waiting for the impacts. Hoffmann expected the familiar sequence: the earth-shaking crashes of shells striking the hillside, the fountain of frozen soil and snow, the ringing silence that followed, and then the shouted roll call to determine if anyone had been hit. What happened instead defied his understanding of artillery warfare. The shells did not impact the ground. They exploded in the air, perhaps 20 meters above the gun position, detonating in perfect synchronization as if triggered by invisible wires. The sound was different, sharper, more concentrated, like the crack of enormous whips rather than the deep thunder of ground impacts. And then the shrapnel came down. Not radiating outward from impact craters but falling vertically, a steel rain that perforated the canvas camouflage netting, punctured equipment, and tore through the bodies of men who had believed themselves safe in covered positions. Hoffman felt something strike his helmet, with enough force to snap his head sideways. He found himself on the ground, ears ringing, vision blurred, tasting blood. Around him, the gun position had been transformed into an abattoir. Men lay motionless in the snow, their bodies punctured by dozens of shrapnel fragments. The gun itself was pockmarked with impact scars, its rangefinder shattered, its traverse mechanism jammed with twisted metal. And Hoffman, staggering to his feet, realized that the Americans had fired perhaps a dozen shells total. A dozen shells had achieved what would have required hundreds using conventional fuses. He was not alone in his shock. Across the Ardennes, German gun crews were experiencing the same impossible phenomenon. Artillery observers reported shells that exploded by themselves in midair. Forward observers, accustomed to directing fire based on observed impacts, found themselves unable to explain what they were witnessing. Intelligence officers, receiving frantic reports from the front, initially suspected some form of acoustic trigger that the shells were detonating in response to sound waves from German guns. But that theory collapsed when proximity-fused shells began exploding above silent positions, above trenches, above any concentration of metal or human activity. Some German soldiers theorized that the Americans had developed sound-seeking shells. Others believed the explosions were triggered by vibrations in the ground. A few, with imaginations shaped by propaganda about Allied technological terror weapons, whispered that the shells contained spirits or demonic forces that could sense German soldiers. The truth, when German intelligence finally pieced together fragmentary evidence from dud shells and interrogated American prisoners, was simultaneously more mundane and more terrifying than any supernatural explanation. The Americans had put radar inside artillery shells. They had miniaturized technology that German scientists had told the High Command would require years of development. They had mass-produced these fuses by the millions and were expending them as casually as conventional ammunition, and there was nothing Germany could do to counter them. The psychological impact of proximity-fused shells exceeded their physical lethality. German soldiers who had endured years of combat, who had developed instincts and survival techniques honed through countless artillery bombardments, found those instincts rendered obsolete. The fundamental calculus of artillery warfare had been: take cover, wait for impacts, emerge when the barrage lifts, continue fighting. Proximity fuses eliminated that calculus. There was no safety in covered positions when shells exploded directly overhead. There was no way to predict safe areas based on shell trajectory. The only effective protection was being underground or inside armored vehicles, and even then, the psychological terror of hearing shells detonate in the air above, knowing that death was raining down with mechanical precision, eroded combat effectiveness as surely as physical casualties. German after-action reports from the Ardennes offensive make repeated references to the new American shells. Unit commanders noted that counter-battery fire had become unnaturally effective, that gun positions were being neutralized with impossibly small numbers of shells, that crew casualties had increased dramatically despite unchanged tactical dispositions. Medical reports documented that shrapnel wounds had shifted from the horizontal fragmentation pattern typical of ground-burst shells to a vertical pattern consistent with aerial detonations. And operational planners, calculating ammunition expenditure rates and casualty ratios, realized that Germany was facing an enemy whose industrial and technological sophistication had reached a level where quantitative superiority had transformed into qualitative dominance. The proximity fuse was not merely a better weapon. It was a manifestation of everything that separated American industrial warfare from German operational philosophy. German military doctrine, even in 1944, retained elements of 19th century thinking about war as a contest of wills, where tactical brilliance and fighting spirit could compensate for material disadvantage. The Germans had developed extraordinary weapons: the Tiger tank, the Me-262 jet fighter, the V-2 rocket, but these were artisanal products, complex machines produced in small numbers by skilled craftsmen. The proximity fuse represented the opposite approach, a technically sophisticated device engineered for mass production, manufactured by the millions using assembly line processes, distributed so widely that individual units could be expended without strategic consequence. By the end of World War II, American factories had produced over 22 million proximity fuses, 22 million devices, each containing miniaturized radar technology, precision timing circuits, and safety mechanisms, each tested and certified for reliability, each packed and shipped across oceans to battlefields in Europe and the Pacific. The scale of production was itself a weapon, a demonstration that American industrial capacity had reached a level where advanced technology could be treated as a consumable resource rather than a strategic asset to be carefully rationed. For German soldiers experiencing the proximity fuse for the first time, the weapon represented a horrifying revelation about the nature of their strategic situation. They had been told that German engineering was superior, that American weapons were crude and unsophisticated, that quantity could not substitute for quality. They had been assured that Germany's technological programs, the jet aircraft, the advanced U-boats, the wonder weapons promised by propaganda, would soon restore military balance. The proximity fuse shattered those comforting illusions. Here was a weapon that combined sophisticated technology with mass production, that worked with ruthless reliability, that was being used so casually that American gunners could expend dozens of rounds to neutralize a single gun position without concern for ammunition supply. Obergefreiter Hoffmann, evacuated from the Ardennes with shrapnel wounds and traumatic hearing loss, would later tell interrogators that the moment he understood what the shells were doing, the moment he realized they contained some form of sensing mechanism that allowed them to detonate at optimal altitude, was the moment he knew Germany had lost the war. Not lost a battle or a campaign, but lost the fundamental contest of industrial and technological capacity that determined modern warfare's outcome. The symbolic power of the proximity fuse extended beyond its tactical effectiveness. Throughout the war, German soldiers had confronted American material abundance in forms both mundane and extraordinary. They had found chocolate bars and cigarettes on captured American positions, luxuries that German soldiers had not seen in years. They had encountered American field rations packed with calories and variety that made German military food seem like starvation fare. They had examined captured American equipment, the standardized components, the precision manufacturing, the casual redundancy that allowed American units to discard damaged equipment rather than repair it. Each encounter reinforced the same message. But these were passive demonstrations of abundance. The proximity fuse was different. It was abundance weaponized, transformed into a tool of destruction that killed with casual efficiency. Every time a proximity-fused shell detonated above a German position, it delivered a message more powerful than propaganda. We have so much technological sophistication, so much industrial capacity, that we can put radar inside disposable artillery shells. We can manufacture millions of these devices. We can expend them by the thousands in a single battle, and there is nothing you can do to stop us. The German military's inability to develop a comparable weapon highlighted the systemic differences between Allied and Axis war economies. German scientists understood the principles of radio proximity fusing. They had conducted theoretical studies and experimental programs, but they could not solve the engineering challenges of miniaturization and mass production. Germany's electronics industry, fragmented among competing firms and agencies, lacked the standardization and coordination that American industry had achieved. German vacuum tube production was measured in thousands per month, American production was measured in millions. German quality control processes emphasized artisanal inspection. American processes emphasized statistical sampling and automated testing. And critically, Germany was fighting a multi-front war with shrinking resources and constant disruption from Allied bombing, while American industry operated in security, with unlimited access to raw materials and a workforce that had grown to include millions of women mobilized for war production. The proximity fuse thus became a test case, demonstrating why Germany could not win a prolonged industrial war against the Allied coalition. It was not merely that America produced more weapons, it was that America could innovate, industrialize, and deploy advanced weapons systems while simultaneously maintaining massive production of conventional arms, while feeding and equipping allies, while sustaining a standard of living for its civilian population that exceeded wartime Germany's peacetime norms. The use of proximity fuses in the Ardennes offensive marked a turning point in Allied tactical doctrine. Once the technology's security restrictions were lifted for land use, American artillery commanders began integrating proximity fuses into standard fire missions. Anti-personnel bombardments shifted from time-on-target salvos, which required complex coordination to achieve simultaneous shell impacts, to rolling barrages where each shell exploded at optimal height as it reached the target area. Counter-battery fire became devastatingly effective. German gun crews found themselves unable to remain in position long enough to conduct sustained fire missions. The tactical adjustments were immediate and profound. American infantry units, which had previously required extensive artillery preparation before assaulting German positions, found they could advance under cover of proximity-fused barrages that suppressed enemy positions without cratering the ground and creating obstacles for advancing troops. The 101st Airborne Division, encircled at Bastogne during the height of the Battle of the Bulge, was sustained not merely by aerial resupply, but by proximity-fused artillery fire that devastated German forces attempting to tighten the siege. And when Allied forces transitioned to counter-offensive operations in January 1945, proximity fuses enabled a level of fire support efficiency that previous generations of artillery could not achieve. German military archives from the final months of the war reflect a growing sense of technological despair. Intelligence assessments catalogued not just proximity fuses, but the entire spectrum of Allied technological advantages: radar-directed anti-aircraft fire, advanced communications systems, proximity-fused naval shells that decimated Japanese kamikaze attacks, air-to-ground rockets with improved accuracy, and above all, the vast logistical networks that kept Allied forces supplied with fuel, ammunition, and spare parts under all conditions. For German planners attempting to devise defensive strategies against the inevitable Allied offensives of 1945, these technological disparities translated into mathematical certainties. Casualty projections showed that German units could not sustain combat effectiveness against Allied forces that possessed multiple overlapping advantages in firepower, mobility, communications, and logistics. Training manuals began emphasizing tactics of delay and withdrawal rather than counterattack and defense. And for the individual German soldier, the daily experience of combat became an exercise in enduring technological superiority that manifested in countless forms, from the American artillery spotter planes that circled overhead with impunity to the proximity-fused shells that exploded with mechanical precision whenever German forces attempted coordinated operations. Obergefreiter Hoffmann survived the war, though he carried shrapnel fragments in his shoulder and back for the rest of his life. In the decades after 1945, he occasionally spoke with historians and journalists about his experiences in the Ardennes. What struck interviewers was not his bitterness, though he expressed frustration at the propaganda that had told German soldiers they were fighting an enemy weak in spirit and crude in methods, but his clinical assessment of what the proximity fuse represented. "We knew they had more tanks, more planes, more shells," he said in a 1978 interview. "We did not know they could put intelligence inside each shell. That was the difference." We were fighting with the weapons of 1943, and they were fighting with weapons from some future decade. Once you understand that, once you see shells that think for themselves, you realize the war is not about courage or tactics. It is about who controls the future. His observation captured something essential about the proximity fuse significance. It was not simply a better weapon, but a demonstration that American industrial and scientific capacity had reached a threshold where the pace of innovation itself became a strategic advantage. Germany could not compete with an enemy that could develop, test, produce, and deploy revolutionary weapons systems within the time frame of a single war. The proximity fuse's technical specifications, declassified in detail after the war, revealed the extraordinary engineering achievement it represented. Each fuse contained a miniature radio transmitter operating at frequencies between 180 and 220 MHz, with a power output of less than 1 watt. The transmitter sent radio waves that reflected off nearby objects, aircraft, ground features, concentrations of metal, and returned to a receiver circuit integrated into the same device. When the received signal strength indicated the shell was at optimal distance from a target, a thyrotron tube triggered the detonator, initiating the explosive chain that detonated the shell's main charge. The entire sequence, from signal transmission to detonation, occurred in milliseconds. The fuse had to arm itself only after the shell had traveled a safe distance from the firing gun, preventing premature detonations that would endanger friendly forces. It had to withstand accelerations that would crush conventional electronics. It had to function reliably in temperatures ranging from Arctic cold to tropical heat, in rain, snow, and humidity. And it had to cost little enough that it could be manufactured by the millions without straining military budgets. American engineers achieved all of this through innovations in vacuum tube design, battery chemistry, mechanical engineering, and production processes that distributed manufacturing across multiple suppliers, with final assembly conducted at arsenals that quality tested every single fuse before shipping. The Pacific Theater provided additional demonstrations of the proximity fuse's capabilities. U.S. Navy ships, equipped with 5-inch guns, firing proximity-fused shells, devastated Japanese kamikaze attacks that had previously inflicted severe casualties on Allied naval forces. The statistics were stark. Ships using conventional time-fused or contact-fused anti-aircraft ammunition required an average of 1,500 rounds to destroy a single attacking aircraft. Ships using proximity fuses required fewer than 300 rounds per kill. For Japanese pilots committed to suicide attacks, the proximity fuse transformed American anti-aircraft fire from a survivable hazard into an impenetrable barrier. The shells exploded as aircraft approached, filling the air with shrapnel that shredded wings and engines, detonating fuel tanks, and killing pilots before they could complete their attacks. Japanese naval records from the final months of the war document the growing realization that kamikaze tactics, which had initially achieved surprise and inflicted significant damage, had become suicidal missions with negligible chances of success. The proximity fuse had not merely improved American defensive capabilities, it had rendered an entire category of Japanese tactics obsolete. And as with German forces in Europe, Japanese commanders found themselves confronting an enemy whose technological advantages had compounded into strategic dominance. The post-war analysis of the proximity fuse's impact placed it among the most significant technological developments of World War II, ranked by many military historians, alongside radar, the atomic bomb, and code-breaking as innovations that fundamentally altered the war's trajectory. But its significance extended beyond military effectiveness. The proximity fuse demonstrated that American industrial democracy could out-innovate authoritarian regimes that centralized scientific resources under state control. The fuse's development involved collaboration between university researchers, private industry, and government agencies, with relatively open exchange of information among scientists working toward shared objectives. German scientific programs, by contrast, suffered from bureaucratic fragmentation, competition among agencies, and ideological interference that prioritized projects aligned with Nazi racial theories over practical military applications. The contrast was not merely organizational but philosophical. American industrial culture valued pragmatic problem-solving and mass production efficiency, while German industrial culture retained artisanal traditions that produced sophisticated prototypes but could not achieve mass manufacturing at scale. The proximity fuse also highlighted the role of American women in wartime production. By 1943, women constituted a majority of the workforce in many electronics manufacturing facilities, producing proximity fuse components. They assembled the delicate vacuum tubes, wound the miniature coils, soldered the circuits, and conducted the quality testing that ensured each fuse would function reliably. These women, many of whom had no technical training before the war, learned precision manufacturing techniques and contributed directly to weapons production that gave Allied forces decisive tactical advantages. Their participation was itself a demonstration of democratic mobilization, the ability of a free society to rapidly train and deploy human resources in response to strategic necessity. German propaganda had insisted that women's proper role was domestic, that modern warfare was inherently masculine, and that societies allowing women into industrial production were decadent and weak. The proximity fuse, manufactured substantially by women and deployed with devastating effectiveness against German forces, provided a practical refutation of that ideology. The symbolic resonance of the proximity fuse extended into the Cold War era, where it became a reference point for discussions of technological competition between superpowers. Soviet military analysts studied captured German reports on proximity fuses and conducted their own programs to develop similar weapons. American defense planners, meanwhile, continued refining proximity fuse technology, developing improved versions for air-to-air missiles, surface-to-air missiles, and eventually smart munitions that integrated multiple sensing technologies. The fundamental principle that weapons could sense their environment and make autonomous decisions about when to detonate became foundational to late 20th century military technology. But the World War II proximity fuse retained unique significance as the first mass-produced smart weapon, the first demonstration that sensing and computing technology could be integrated into expendable munitions. Every guided missile, every smart bomb, every autonomous weapons system developed in subsequent decades traced its conceptual lineage to those 5-inch shells that exploded above German gun positions in the Ardennes forests. For the individual German soldiers who survived encounters with proximity fuses, the weapon left psychological scars that persisted long after physical wounds healed. Veterans interviewed decades later recalled the helplessness they felt hearing shells detonate overhead, knowing that cover and concealment offered no protection, that survival was purely probabilistic. Some described the experience as confronting a malevolent intelligence, as though the shells were hunting them personally. Others spoke of it in more abstract terms, as the moment they understood that German military power, which had seemed invincible in 1940, had been surpassed not just in quantity but in quality, sophistication, and innovation. The proximity fuse forced German soldiers to confront a truth that propaganda had denied, that democracy, far from being weak and decadent, had proven capable of mobilizing scientific genius and industrial capacity on a scale totalitarian systems could not match. And that realization, more than any battlefield defeat, shattered the ideological certainty that had sustained German military morale through years of war. The ethics of weapons development emerged as a post-war debate, shaped partly by the proximity fuse's success. Critics of strategic bombing and atomic weapons pointed to the proximity fuse as an example of a weapon that increased military effectiveness without causing disproportionate civilian casualties. Unlike area bombardment or nuclear weapons, proximity fuses improved precision and efficiency against military targets. Defenders of Allied strategic policies argued that the fuse demonstrated the difference between weapons designed to terrorize populations and weapons designed to defeat enemy forces efficiently. The debate continues among military ethicists and historians, but the proximity fuse's tactical role remains relatively uncontroversial. It was a weapon that allowed Allied forces to neutralize enemy positions with fewer rounds, reducing both the duration of combat and collateral damage, compared to saturation bombardment with conventional fuses. In that sense, it represented a kind of humanitarian technological progress, a weapon that killed more efficiently but also more discriminately, directing lethal force against combatants rather than landscapes. The final months of World War II saw proximity fuses deployed across every theatre where American forces operated. They supported the Rhine crossings in March 1945, providing suppressive fire that allowed engineers to construct pontoon bridges under enemy fire. They covered the final offensives into Germany, neutralizing German rearguard positions and counter-battery fire. They supported Pacific Island assaults, protecting landing craft and beach positions from Japanese artillery. By the time Germany surrendered in May 1945, American artillery units had expended millions of proximity-fused shells, and the weapon had become so routine that its use was noted in after-action reports with the same casualness that previous generations of reports noted the use of high-explosive or smoke rounds. The proximity fuse had transitioned from secret weapon to standard tool, from technological marvel to ordinary equipment. And that transition itself testified to American industrial and logistical capacity, the ability to produce revolutionary weapons in such quantity that they became conventional. In the end, the German gunners' astonishment at shells exploding above their positions was not merely surprise at an unexpected weapon, but recognition of a deeper truth about the war they were fighting. They had believed themselves part of a military force representing Europe's technological and cultural pinnacle, fighting against a nation they had been taught to view as materialistic and spiritually weak. The proximity fuse, that compact cylinder of electronics and explosives, refuted that belief with every aerial detonation. It demonstrated that American democracy had mobilized scientific talent, industrial resources, and human ingenuity on a scale that rendered German technical achievements obsolete. It proved that a free society could innovate faster and produce more effectively than authoritarian control systems. And it revealed, in the most tangible way possible, that German soldiers were not fighting against an inferior enemy, but against a nation that had mastered the fundamental challenge of modern warfare: the integration of science, industry, and military doctrine into a system capable of continuous innovation and overwhelming material superiority. The shells that exploded above frozen forests in December 1944 carried no messages, bore no markings explaining their function, offered no warnings before detonation. They were silent emissaries of a technological revolution, anonymous products of assembly lines staffed by workers whose names would never appear in history books, tools of a war machine that had industrialized not just production but innovation itself. For the German soldiers who survived those explosions, the proximity fuse became a symbol of everything they had lost, not just battles or territory, but the illusion of technical parity, the belief that courage and tactical skill could overcome material disadvantage, the propaganda-sustained myth that Germany was fighting enemies who lacked the will and capacity to prevail. And for historians examining the war's technological dimension, the proximity fuse stands as evidence that World War II was decided not merely on battlefields, but in laboratories and factories, in the organizational systems that could translate scientific discovery into mass-produced weapons, in the democratic societies that trusted their citizens with education, innovation, and the collective project of defending freedom against tyranny. The winter snow that fell on the Ardennes in December 1944 covered shell craters and abandoned gun positions, erasing the immediate evidence of battle. But the memory of those aerial explosions, the sound of shells detonating overhead with mechanical precision, lingered in the minds of men who had witnessed the future arriving in the form of weapons that could think, sense, and kill with automated efficiency. They had seen the endpoint of industrial warfare's logic, the transformation of human ingenuity into tools of destruction so sophisticated that individual soldiers became irrelevant. their courage and training nullified by machines that executed their lethal functions without hesitation or mercy. And in that transformation, in the terrible effectiveness of shells that exploded on command from electronic circuits smaller than a man's fist, the German gunners glimpsed the world that would emerge from the war, a world where technological competition among nations would determine strategic outcomes, where scientific innovation would drive military doctrine, and where the capacity to produce smart weapons in unlimited quantities would separate victors from the vanquished. The proximity fuse was not just a weapon. It was a herald of the century to come, delivered by artillery fire to soldiers who still fought with the assumptions of an earlier age, exploding above their positions with the message that the old world had ended and a new one, governed by different rules and dominated by different powers, had already begun.